Welcome to RF transceiver design course. We are discussing a low noise amplifier and we are in module 7 lecture 40. We discussed in the last class what are the different configuration, basic configuration, common source, common gate and common source with source degeneration inductor. All these low noise amplifier we have tried to find out input impedance, output impedance, its gain and noise figure. We will discuss all these uh, in further, that what are the different topologies that can be possible by using this all the topology. So, what we have discussed up to now, that is a common source amplifier with source degeneration. Now with inductive source degeneration. So what we have done initially, we have tried to do the impedance matching by using a resistor, but resistor is adding a too much noise. So we try to make the input impedance resistive by using a inductive source degeneration technique. That will help us to get the impedance matching as well as reducing the noise figure. So that we have already done. So this is a without using a cascode and this is a with using a cascode. So what happens, as discussed in the last class, that an inductive load introduce a negative resistance. So because if there is a this inductor and this CGD capacitor, due to this there is a negative resistance and that will make the our amplifier unstable. And as we have discussed in the stability, that we do not want a negative resistance to happen in our amplifier. That is why in order to reduce that, in order to remove that negative resistance, we can use a cascode. So this is a cascode structure, that is where we use another transistors with common gate. So this is a common source followed by common gate configuration, and it will also help us to isolate the input and output. So as we have discussed in when we have tried to design a low noise amplifier by using a S parameter method, in that we try to make S12 is equal to 0. So that is a unilateral. So if the isolation between output and input is better, you can consider it as a more unilateral. And while designing this structure, you can also make by using a S parameter method only these two ports. This can be divided in two ports, and based on that you can find out the uh, whatever S parameter is available, you can find out the input and output matching network. So that is a method mostly used at high frequencies, and we can also use the same device topology approach to design the low noise amplifier. It has a input matching is the same as a common source LNA. The gain is high. We already know that cascode will provide a higher gain. It has a better reverse isolation. The noise figure is same as a common source low noise amplifier, and as discussed, it will provide the much better stability, but it suffers from the nonlinearity because the amount of headroom that you required to have this transistor in saturation will reduce, and that is why overdrive voltage is reduced and it will lead to non-linearity in your circuit. So this is however, but it is a widely used LNA because it has all the advantage that required in the LNA, low noise amplifier design. We will try to see the other topologies based on the other configuration. So before going to the other topologies, how we can try to design. So what should be the design procedure for inductive source degeneration? Uh, LNA. So, this is a common source LNA with inductive source degeneration, and how can we design? So, first of all we need to identify or the specification. Let us say what is the frequency of operation, and then what is the gain that we required, what is the power consumption, what is the application. So, all these specification needs to be worked out before designing the low noise amplifier. Then second is the technology. So, which technology you are going to use, because based on the technology your omega t is decided. Let us say for lower node higher node technology where there is a length is high, the FT is low. In lower node technology the FT is high. So, in that case the noise figure you can achieve here, the noise figure that we require, that is also one of the parameter, and that can be find out based on the sensitivity. So, sensitivity is a parameter, it is provided in each standard. So, if you remember when we discuss the basic of wireless communication, in that we discuss about the sensitivity, and if the any standard has provided the sensitivity based on the required SNR, you can find out the noise figure of your receiver, and as LNA is the first component you will get the noise figure of low noise amplifier. So, all these parameters are important, and once you know the specification and technology, you need to find out the width of the MOSFET. So, you can use a power match equation, that W opt equation that we have already discussed in one of the lecture. Then we can also use a GMID plot for finding out the width based on the required power consumption. We can also use another method which is widely used to design an amplifier, that is GM by ID versus ID by W by L method. So, this method will provide the optimum width for the region of operation. You can also design your LNA in a sub-threshold region, in saturation, weak inversion and a strong inversion. So, this all three in all three region we can design by using this GM by ID versus ID by W by L method. Then we need to find the value of Ls by using this formula. Now, here we have also considered the pad capacitance, because always in the when we design a circuit on chip we need to consider the pad. So, if your gate is connected to the any pad, it has a certain pad capacitance that is given by a C pad, and that should be considered while finding out the value of Rs. If you do not consider this, then we can directly write the Rs which is equal to omega t Ls, but it is important to consider the pad capacitance. Now, we need to find the value of Lg. So, we know the frequency of operation, and based on the frequency of operation, so first we find out the Ls, we based on the biasing and the technology. So, this you will get from biasing, and this is provided by technology. Pad capacitance, so this is already known, this is also already known, Ls is also known, omega naught is known, you can find the value of Lg. Then we also need to find the value of Ld, because here this Ld is also have a many capacitors. So, the capacitor which is coming here is a CGD, and then there is a CDB capacitor, and there are output capacitor which is going to drive. So, because when we are designing a low noise amplifier on chip, what is happening, that the next stage might be the mixer or any other filter that we have designed. So, mostly on chip the next stage will be mixer, that mixer or buffer, if you are keeping the buffer in between, that your LNA should drive that much capacitance of the next stage. So, that is the value of omega naught. We will get the LD by using this omega naught square. So, the here we have considered CGD, CDB and output capacitance and the LD. We will get, so once you have find out the all the values of the in the topology, that is common source LNA with inductive source degeneration, we can make the circuit. We also need to make a biasing. So, there are various biasing circuits can be employed which can help us to bias our low noise amplifier. So, this is how we can design a low noise amplifier. This is a common source LNA design procedure. Same we can also use a common gate LNA. The only difference in the common gate is we are giving the input to the common gate, and while designing a common gate there is a one inductor is used at the source side here also, and that inductance should have a resonance at your desired frequency. And the advantage of this common gate versus common source is it will provide the wide band matching. However, the noise figure is a little higher compared to the this common source LNA. Otherwise, the methodology will remain same. First, we need to identify the width, and here one more thing, that our input impedance is equal to 1 by Gm. So, this Gm should also be around 20 millisiemens, so that you will get a input impedance of 50 ohm. We can also use a, instead of RD, we can also use a LD. This is V bias, this is V in, this is V out. The same as a common source LNA, we can also use a LD, and you can find out the value of LD. So, this is how the basic configuration of common source and common gate can be designed. So, we can also make another topology, which is a common gate with feed forward LNA. So, in that we will do the feed forward from to the gate to the input side, that is one amplifier can be used additionally. So, what is the disadvantage of the normal common gate LNA? The disadvantage of the normal common gate LNA is your input impedance is have a direct relation with a Gm. So, and we already know that this Gm is also responsible to give you the lower noise. So, if we try to decouple this, and this is a two method, that is a feed forward and feedback. By using feed forward and feedback, we can decouple the input impedance only depend upon the Gm. So, here Z in is given by 1 by Gm into 1 plus A. So, input impedance is reduced by factor of 1 plus A. So, we can increase the value of Gm, and that will also increase the gain, and it will reduce the noise figure, and gain is increased by factor of 1 plus A, and noise is reduced by 1 plus A. So, this is a noise figure which is given by gamma by 1 plus A plus 4 by Rs into R1. Now, this R1 resistance, as I told multiple times, because there are capacitance here, inherent capacitance of MOSFET as we have discussed in the last slide, and because during the resonance there is a and this is not all ideal inductor. So, there is a resistance which is a R1, and during the resonance that resistance will be there. We can also keep a separate resistance, high value resistance, in order to get the higher gain. However, it will suffer from the your quality factor, means your noise will increase. So, this is how we can design a feed forward LNA. We can also design a common gate LNA with a feedback. So, same thing, it will decouple input impedance and noise factor, and noise figure is the same as a common gate LNA. So, there is not much difference in noise figure, but what is the advantage? Because there is a decoupling, you can increase this term Gm into Rs, and if you increase this term Gm into Rs, your noise figure can be reduced. So, this is a improved topology of common gate LNA. We can also have a resistive feedback noise cancelling LNA. So, while designing a resistive feedback noise cancelling LNA, we already have discussed this LNA. This we have already discussed. Now, if we can make in our circuit a 2 node where a noise is same, noise polarity is the same, but the signal is inverted. So, if we try, so what is happening that here at Y the noise is both the noise are same at Y point. However, the signal X is also whatever signal is coming is going to inverted. So, if we try to make this another auxiliary amplifier, what it will do, that it will nullify the noise generated due to transistors as well as this RS resistor. So, that while doing the addition or subtraction, if we have a polarity of noise is same, if we are doing the subtraction, if the polarity of noise is same and polarity of this amplifier and this amplifier is a different, then we will get the addition in the signal and subtraction in the noise. So, here signal should be a different sign, our signal should be of different sign and noise should have a same sign. So, when we take a difference, we will get the output which is a noise cancelled. So, that is why it is called a noise cancelling LNA. So, here by increasing the value of RF, gain can also become high, and another important thing here, you require an auxiliary amplifier. So, this auxiliary amplifier should mimic the actual low LNA, actual amplifier. If it is not providing the same gain, if it is not if it does not have the similar gain, then the cancellation, you will not get the complete cancellation of the noise. So, this is depend upon the how the both amplifier are matched in terms of the gain. So, but however, it will reduce the noise factor, and in many application this can be used because this circuit does not require the inductor, and without the inductor you can design the this LNA. So, that is why this is also called the inductorless LNA. Now, we will see the balloon LNA, because that is also one of the important design. What is a balloon? So, there are two kinds of balloon, passive and active. We can use passive circuits to give you the single and two differential signal, and it is passive is a lossy and it will be narrow band, and it is a costly also because you need to use off chip, or if you are using inductor or capacitor to design a balun or a transformer, it is very it will take too much size on chip. So, that is why passive balun are not that much widely used. However, it can be used if you are going for very high frequency, and then transformer, designing a transformer will don't require too much space, it will have a reduction is in space because lambda is reduced, and that is why we can also make a passive balun on chip. But if we are working at lower frequency, we can also think of active balun, because and why if balun is important, our antenna is a single ended, and this single ended, if we want to convert to differential, because we already have, so this is a single ended, and if you want to convert into the differential, and if you are so this is a, as here written, single ended to differential. So what is the advantage of making a differential? We will have the benefit of improving the linearity. We already discussed that we can have a better IP2 or second order linearity if we use a complete differential design. So it will also reduce the it will also cancel out the common mode signals, like if there is a LO feed through, that can also be cancelled out. So that is why active balun is also important, converting single ended to differential signal. So in active balun, it is a low loss, it will only consist require two uh, transistors, it is it will provide high power gain, and it will have a low noise over the wideband. So how can we design the single ended to differential? We will take advantage of both common gate and common source low noise amplifier. So this is a combination of common gate. So here what we have a common gate amplifier, and this is a common source amplifier, and when we have both common gate and common source followed, because common gate has a positive gain and common source has a negative gain. So at this point you will have a differential signal. So this is a positive and this is a negative, but we need to make sure that the gain of the common gate is equal to gain of the common source. So all noise and distortion generated by common gate transistors can be cancelled out, and as if we try to see the input impedance at this side, it is mostly 1 by GM, because this is a high impedance, common source has a high impedance. So and that is why it can provide the very wide band. Overall linearity of a complete LNA determined by the common source and common gate means both common source LNA, because here this will have a higher overdrive voltage, and advantage is here you can directly cancel out the second order harmonics, and final noise is determined based on the CG and resistance CG and resistance at the common source side. Gain should be equal, and overall linearity of a complete LNA determined by this common source LNA. So this is the same sentence. So final noise determined by this both the value. So what is the drawback? Noise generated by common source stage is significant because of its low transconductance, and transconductance of common source amplifier need to be scaled by n. So that if we try to improve, so if you make GM into CG and if you scale it by down by n, and same thing if you scale this also by the resistance also by n. So what you need is GM into GM of the common gate is equal to n into GM into common source, and resistance RCA is equal to R common gate by n. So noise contribution of common source decreases with a factor of 1 by n for increasing the n, and voltage gain remain a constant. This topology is also very widely used to convert a single ended to differential signal. What is the drawback? Gain and phase imbalance at the differential output. It does not have means symmetrical load, and it is using a current bleeding technique, and above technique imbalance is sensitivity to the PVT, because the GM of these is different than GM of this, and what will happen that if there is a process variation, you cannot get the uh, differential signal which is of the 0 and 180-degree phase. There is a mismatch in the uh, so gain and phase imbalance will be there. So that is why common gate and common source balloon LNA can also employing a current bleeding technique. So that this is a current bleeding circuit can be used, and that current bleeding circuit here ID of common source is equal to I, and IBLD is equal to n minus 1 I. So here symmetric load, because current flowing through RCG is equal to RCS, then this and this will be remain same. So what is the drawback of this? Balance output at the cost of worse of noise figure, because you are adding a more and more transistors, and that increase the noise figure. So it is a more noise figure, but we can have a advantage in terms of the gain and phase balance. We can have also modify current bleeding circuits where noise contribution of MB can also be reduced. That can also be reduced by using this technique. What is the advantage? It achieves a performance improvement in both noise figure and as well as output balance. Inductorless LNA, we already have discussed 1 or 2 LNA. So that is a common gate by using a common gate configuration that can also be clubbed into this inductorless LNA. So traditional LNAs with on-chip inductor occupy very large area, and counter benefits brought by scale to digital CMOS. And there is a lack of inductor modeling in many technologies, and it complicates the circuit design. So if you do not desire very low, means too much, if your sensitivity is not stringent, then you can use inductors without inductor low noise amplifier, and off chip inductor also can be used. It has a high Q than a cheap inductor, but what is happen, it increase the cost, reduce the yield, because you need to use the off chip inductor. It will also increase the size. So that is why this can not be advantageous in terms of using a off chip inductor, but for many application it can be used. So it depends upon the application what you try to design. So we already have seen this common source LNA with active feedback. So we can use a active feedback here. So this is nothing but feedback that has been employed at the back side, and then by using active feedback we can have a better means performance in terms of the noise as well as in terms of the linearity. We can also have a gain boosting technique that will boost the GM. So how the GM boosting technique has been used? So let us say here there is an input, and this is a positive negative. So this is a differential circuit. So this is a here you are using a common gate configuration, and same signal you are also applying to the common source configuration. So here your GM is multiplied. So the same signal here you are getting a input signal at the source as well as input signal at the gate, and because of that your GM is multiplied by 2 times, and that will improve the gain. And as we are increasing the gain or GM, because in this configuration our GM is in denominator, means if we find the noise figure our GM is in denominator, and if we try to increase the GM, the noise figure, so noise figure is inversely proportional to GM. If we try to increase the GM, our noise figure will reduce. So here the voltage gain still restricted by input matching condition. So this input matching, because you cannot have GM more than 20 millisiemens, because then we cannot have a 50 ohm impedance matching. So, various approach can be used to make the different topology. You can also design your own topology which will have the better performance compared to all that we have discussed. We can have a different voltage combiner in order to improve the linearity. So, it is used to combining a differential output single to differential converter. So, this is input, and what we will get a diode connected load, plus we can get the V in and VB. So, this is output. So, if we try to combine both this configuration, so what is we are doing is, at this point we will have a output which is a combined voltage combiner. So, voltage combiner circuits are also widely used. What is the disadvantage of common source with a diode connected load? It shows the poor third order harmonic distortion performance, and disadvantage of a source follower, it is a second order and third order harmonic distortion is reduced by a factor of a large loop gain. So, various configuration can be used to do the voltage combination, and we can use a inductorless LNA with a voltage combiner. So, here the voltage combination combining has been done, and that will help to improve the uh, linearity performance, because up to now we have not discussed the linearity, but linearity is more linearity we will get if we try to use a differential configuration. So, it achieves the more power efficient, noise figure and high voltage gain. It provides linear feedback operation with second order and third order equal to 0. And off chip low noise and bulky inductor can be used to reduce the noise contribution, and advantage of inductor less is a discounted. So, this has here there is a inverting path, this is a non inverting path, and that will be combined so that you will get the final output. This is a inverter based inductorless LNA. So, we can also use the inverter as an amplifier. So, here this configuration is nothing but inverter as an amplifier. So, if we try to consider the inverter, this is the inverter, and if we try to bias, if you want to make a constant bias, if we use a feedback, that will, this is nothing but to maintain the bias at this point where both the transistor are in saturation, you will get the, you can use this as a amplifier, and this configuration can also be derived the same as what we have discussed. So, the input impedance, what we have discussed, the resistive feedback common source amplifier, R in, which is R out plus RF 1 plus Cm into R out, where R out is nothing but RO1 parallel RO2, and Gm is nothing but Gm1 plus Gm2. So, this is a voltage gain, that is R out by 2 Rs 1 minus Gm Rf by 1 plus Cm R out, and this is a noise factor. We can also have a classification of LNA based on the different application. So, we will discuss about the classification in the next class. Thank you.